Good morning, everybody. Welcome to this webinar on Yaskawa's Regenerative Drive Solutions. I'm Christopher Gesult, Product Manager for Yaskawa's Regenerative Drive Solutions. Today's presentation will cover regeneration, Yaskawa's solution for regeneration, and an understanding of how to size each of these product offerings. And finally, an overview of our regenerative products themselves. First up is regeneration. So what is regeneration? Regeneration occurs in processes that restore, renew, or revitalize their own source of energy and material. Well, what does that really mean? Let's put that in terms of drives and motors. So regen, how does it happen? When a motor turns a load, it consumes energy. Like when you're pushing on a door to open it, it's going to take some energy to move that door. However, when a motor is turned by the load, it regenerates. The motor turns into a generator. Think of another person trying to open a door, but you're resisting them. They are doing all the work, you're just holding back. Your holdback is that regen energy. This energy flows back to the motor and into the drive, and the drive needs to do something with it. But when does that happen? When does regen occur? You have overhauling loads like elevators and unwinders that are constantly in regen. You have unstable or cyclic operation where motors go in and out of regen constantly, like washers and dryers. And finally, you have forced deceleration, which is pretty much any application that requires stopping the motor quicker than it would coast. Now, each of these applications can be reclassified into three categories: light, medium or heavy, and then continuous. The first is light duty, which is basically all forced deceleration applications. Again, forced deceleration is whenever regen occurs due to you trying to stop the load quicker than it would normally coast to a stop. Medium and heavy-duty applications are the oscillating unbalanced loads, pump jacks, rams, mixers, and continuous regen loads are loads that continuously regen. No brainer there. We'll bring this list up later in our presentation, and it'll come in handy when we're sizing some of our drives. So here's a regen example. So we have a downhill conveyor, and we have an A1000 here running that conveyor. So our direction of travel is down, obviously, and to the right. And when we're running the motor, it's going to put output current, or the motor is going to pull current from the drive to create that directional shift for the conveyor. Let's put some potato-sized loads on there. And what's going to happen is the load of the belt and the loads themselves are going to be forced down by gravity. So those loads are going to want to drag that conveyor to go faster. What the drive is going to do, it's told to go a specific speed, so it's going to hold back. It's going to try to maintain that speed you command it, not let gravity pull it forward. So it has that hold back torque to maintain the speed you commanded it. While holding back, that's when regen occurs. Now there are actually 4 quadrants of operation. In any application, you can go forward and reverse. You may not want to, but you can. In each of these directions, the motor can be motoring or use power, or it can be in regen, it can generate power. You have your typical quadrant here. You have your motoring, your forward direction, where in this case you have a counterweight. You have a counterweight here, and then you have the load itself. So you're trying to go in this direction. Your counterweight is pulling you back, so you're going to create motoring energy to go in the forward direction. In regen, and assuming you have an unloaded load itself, your counterweight itself is going to be heavier, so that's going to pull you down. Your direction is in that same direction, so what the drive is going to do, it's going to have to hold back and create regen. So that's all in the forward direction here. Now, as I said, you can also reverse in regen. So if you're trying to go the opposite direction and you're loaded, it's going to pull you down, so the drive itself is going to want to pull back. You're going to be in regen. So the point of this slide is to say you have 4 quadrants. You can be in regen both in the forward direction and in the reverse direction. Just depends on how the load is situated with respect to how you're trying to operate it. So why worry about regen? Let's look at a regular drive. From their advantages perspective, drives provide motor control, energy savings, and have very good displacement power factor, all in a very compact size. However, their input current can contain high harmonics. This leads to poor distortion power factor and a limited true power factor. When it comes to today's topic, standard drives have no built-in regenerative capabilities. So when you're looking at power flow, you can see the power flow of a standard drive. Motoring power is generated by converting AC power to DC through the DC bus, and then the output switches of the drive take that DC and convert a PWM AC waveform to operate the motor. When in Regen, the diode bridge, right here, is only a one-way acting device. Basically blocks any regen coming back onto the line from the motor and onto the DC bus from going back onto the line. Without extra hardware, the DC bus will build up during regen until the drive faults on DC bus overvoltage. By having regen, you're giving yourself a nuisance trip or basically an application that will not operate continuously. So drives, it can become commonly confused that drives can handle some sort of regen. It's not really true. Drives, any regen these drives can absorb is really due to system losses. Motor losses, mechanical losses, drive losses. Typically about 10 to 20% of the system rating can be handled by the overall system. It's when you go beyond this that you need to be able to dissipate that extra energy. So what solutions does Yaskawa offer for regen? Let's take a look. The most common method of dissipating regen is to burn it off using braking resistors. The advantage of this method is cost and possibly simplicity. Smaller drives have an extra built-in switch to divert the extra energy, extra power, to a resistor. Therefore, all you need with these types of drives is an external resistor to burn off that extra energy. A very simple concept. However, if you have a large amount of regen, or the drive doesn't have built-in braking switch, then you need one or more external switches and resistors. The bottom image here shows you what a more complicated external braking package will look like. Bottom line is these options waste energy, plain and simple. They burn off extra energy as heat, kind of like a toaster. Additionally, the heating element presents a safety risk if combustible materials were to fall onto or nearby the hot resistor elements. Essentially, you're creating a fire risk. Also, the drive's internal braking switch is limited in its usability. What do I mean by that? Usually these internal braking switches are typically rated for 10% duty cycle. That means these packages can get quite large and complicated, like the image below here, if you need large amounts of regen to be dissipated. Next up, we have our first green regenerative solution. This solution is called a fundamental front end, or an FFE. But what is an FFE? Well, that's just a fancy name for our R1000. The R1000 will take the extra energy and put it back onto the line using a 6-step voltage waveform. This means we can now save energy. No more waste. However, since we do it with a minimal amount of input filtering, we're going to have some current harmonics on the input current waveform, typically 40% ITHD. We also need a few more components to make this work. We need an extra module, the R1000 itself, some fusing, and some reactors in place. We also need a drive to actually run the motor. So the initial costs of the R1000s are expected to be a little bit more than your braking packages. Here's an example of the power flow for the R1000. As you can see, the drive itself still handles the motoring power. However, during regen, the power is diverted from the DC bus through the R1000 back onto the line. So the R1000 needs only to be sized for applications regenerative energy needs and not the motoring power itself. Motoring power is taken care of by the drive. The R1000 does not need to be sized for the motor horsepower. The next option for regen is an active front end, or an AFE. Yaskawa's AFE is the D1000. The D1000 is comprised of a regenerative converter and an input filter. There's your converter, there's your input filter circuit. The D1000 provides a DC output for the drive running the motor. Unlike the R1000, the D1000 is in line with the drive's power. This means the D1000 has to supply both motoring and regen power. Like the R1000, the D1000 saves energy. It saves energy by putting it back on the line. However, the D1000 uses a PWM waveform, not a 6-step waveform. That PWM waveform is filtered to keep the input harmonics lower. The D1000 will keep the input harmonics to less than 5% at the input of the drive during rated power conditions. Like the R1000, we still need a drive to run the motor. The added components and wiring makes the D1000 package larger and more expensive than the R1000. The ideal use for the D1000 is common bus configurations, but we'll get to that in a little bit later in the presentation. Again, here's the power flow I mentioned. As you can see, the D1000 handles both motoring and regen power flow. The D1000 converts AC to DC. The drive itself converts that DC back to AC to run the motor. When regenerating, that extra energy is put back onto the DC bus, and the D1000 uses its PWM waveform, and with that filter, provides a nice AC waveform back onto the line. Again, that harmonic content is left at less than 5% ITHD at full load. Some people like to think of the D1000 as a big DC power supply, or just a big fuse. Either way, they're not too far off in its capabilities. We talked about waveforms. I mentioned PWM and 6-step, but what are they? Above here, you see an example of a PWM waveform. The PWM waveform for the D1000 is generated by tracking the AC input voltage and then using a reference sample waveform that's overlaid that. Whenever the input signal is higher than that reference signal, we basically just generate a pulse, or the output, that DC, is sent to the line. The PWM is filtered by the input PWM filter, and then what results is the two waveforms on the right here. You can see the voltage waveform in purple, and then the nice sinusoidal waveform in green is your input current waveform. So again, both are very sinusoidal. As I said previously, the R1000 does not generate a PWM waveform. Instead, it's a 6-pulse waveform. Essentially, each output phase, so if you consider VAO here as your R, VBO as your S, and then VAB here is your R and S. So you got your per phase voltage here, and then you have your line to line here. So you could see that with VAO and VBO, they basically just turn on and off consistently. So essentially, each output phase will simply turn on and stay on when needed. The combination gives you a very crude line-to-line sine wave, as you can see here. I'll trace it with a pen. So you can see the sine wave here that's generated with the 6-step waveform. However, it's not a true PWM waveform or true sine wave, so what you'll get is the resulting current waveforms on the right here. So you can see that the red, the blue, and the green represent the input current waveforms that the R1000 will generate. Similar to a standard drive, but hardly sinusoidal, hence the 40% harmonics during regen. The last regen option is the Yaskawa's matrix drive, the U1000. I'll try to consistently use U1000 going forward, but please be aware that when I say matrix, I mean U1000, or if I say U1000, I mean matrix. It's one and the same product. The U1000 can provide motoring power and regen power in an effective, all-in-one, compact, low harmonic package. Wiring and installation can be simplified using the U1000. A simple 3 wires in, 3 wires out. In all the previous packages, you have to add components to reduce harmonics. The U1000 draws low harmonic current naturally as it runs the motor. That's right. I said as it runs the motor. You don't need another drive to run the motor. The capability to run a motor is already built into the U1000. So let's break down each solution. On the left-hand side, you can see each of the solutions. You have the braking resistor configuration, you have the R1000 configuration, and you have the D1000 configuration, and finally the matrix or the U1000 configuration. As you can see, the matrix drive does not have a separate VFD like the other solutions. All of these solutions handle regenerative energy. It really depends, so what solution is best? It all depends on what your additional needs are. And I kind of have a few of them listed above. Low harmonics, high power factor, regeneration, and compact size. So braking resistors, when they're small, they're economical and they're usable. However, when they get large, they can be large and they burn off your extra energy, so nothing is really saved. So they don't provide any improved power factor or reduced harmonics. So that leads you to the R1000. The R1000 package regenerates energy back on the line. It saves energy, but they can be larger than braking packages, and it does nothing for improved power factor or harmonics. Which brings up the D1000. The D1000 offers low harmonic, high power factor regen solution, but it's larger and can be more complicated than the R1000. The U1000 is the best overall solution. It is a low harmonic, high power factor regen solution in a simple, compact configuration. Now that we know a little bit about our regen products, let's talk more about the R&D. If you want to learn more about the U1000, we have several cafes and a YouTube video that goes over its features and benefits. just visit our website at yaskawa.com to learn more. The R1000 and D1000 look alike, but they are fundamentally different. I threw in the U1000 here just to show you how it compares to the other units. To start, what runs the motor? Not the D1000, not the R1000. You'll need a separate package to do that. Only the U1000 also runs a motor while it handles the regen capability. You need a separate drive to run the motor with the D and R1000. Again, they all can handle regen, or we wouldn't really be talking about it today. The R1000 only handles regen, whereas the D1000 and the U1000 handle both motoring and regen power. When in regen, the waveforms are different. The R1000 is a 6-step waveform. As a result, it's going to have a 6-step current like we showed previously, harmonics 40 to 50% ITHD. The D1000 is going to generate a PWM waveform. That waveform is going to be cleaned and filtered by that input filter. So it's going to have a nice sinusoidal AC current with less than 5% ITHD at the input terminals of the D1000. I mentioned the D1000 is a DC power supply, and as such, we can regulate that DC supply. The R1000 is a simple converter, so it's just going to take that DC and put it back on the line, so it's not going to regulate it. And obviously, our matrix drive control is just an AC to AC converter. There is no DC bus there. The last difference between these units is common busing. The R1000 and U1000 are really for one-to-one configurations. However, the ideal use for the D1000 is in common busing. Since it has a DC output, it can feed one or more devices. So what do I mean by common busing? I mentioned the D1000 is a big DC power supply. So, using an oversized D1000, you can not only run a one-to-one configuration, a D1000 running one drive with a motor, you can also feed that DC to several drives as long as that D1000 is sufficiently sized. Here's the typical layout of the D1000 versus the R1000. The D1000 has the D1000 converter itself. It has a reactor and a filter circuit, an LC circuit. The R1000 configuration, again, you have the R1000 itself, and then you have two reactors, and there's also some fusing here that's not shown. And again, just to reiterate, we still need a drive or an inverter to run that motor. There's actually 3 versions to the D1000 package. There's a small, there's a large, and then there's an XL. Each comes with the D1000 converter. The change is in the input filter circuit, as I've kind of highlighted here in light red. The small configuration contains a filter module and an external reactor. So there's your reactor, there's your filter module. This is what converts that PWM into an AC waveform. The larger package splits out that filter into individual pieces, made of 3 reactors and a capacitor. So this filter circuit, what I'm saying here is this filter circuit is split up into this reactor, and this capacitor. So now we have basically components that make up the entire circuit. This small package up here on the top is used for essentially all D1000 packages, except for the largest 3 480 volt modules. The large package is used for the 300 and 400 horsepower 480 volt D1000 packages. If you notice here, we have phase detection circuits that go into the line. These phase detection circuits are key to the operation of the D1000. The misconnection of these detection circuits is the leading cause for D1000 installation and startup faults. The R1000 also has these phase detection circuits, so they're crucial in making sure that OV and OC is overcome. Essentially, if you make sure that your installation is clean and done properly, these things power up and run immediately. Now, I mentioned an XL configuration. The XL configuration is similar to the large one. The only difference is that the reactor right before the drive is split into 2 reactors instead of 1. This allows us to significantly reduce the size of the reactor right before the drive. This configuration is only used on the largest D1000 package, the 750 horsepower 480 volt unit. One last time, let me point out those phase detection circuits. They must be phased correctly, so your incoming R lead must be tied to little r. Your incoming S lead must be tied to little s, so forth and so on. OV and OC, as I mentioned, can occur if it's not connected properly. Just imagine trying to regenerate back on the line onto the wrong voltage supply. It's going to easily create an OV condition or an OC condition. So let's discuss selecting our regenerative options. The first option anyone thinks of for regen is dynamic braking. However, if you want to save energy, then the R1000 is really your first choice. If you want low harmonics, then use the U1000. Yes, I said U1000. I skipped the D. The U1000 can do what the D1000 can do and more. The only time I would recommend using the D1000 is if you have a common bus configuration. Why add all the complicated extra components when you can achieve all that and more using the all-in-one U1000? So let's size each of these one at a time, starting with dynamic braking packages. There's essentially two main criteria for sizing dynamic braking: peak braking power and the wattage the resistor can handle. Resistance determines the peak braking power. The lower the resistance, the higher the peak braking power a resistor can dissipate. Wattage determines your average braking power. This is the amount of energy that the resistor must dissipate over the entire run cycle. The combination of these two is how you select your resistors. Braking resistor selection is all based on regenerative duty cycle. The duty cycle is essentially the amount of time the motor is in regen versus the time it is not. This is represented as the on and off times in the above chart. On is when the motor is in regen, and as you can see, off can be idle, powered down, or motoring. Basically anything but regen. 90% of all regen applications have low duty cycles, essentially 10% or less of the overall cycle. 10% duty cycle or less is what I'm trying to say. When it comes to selecting these, Yaskawa makes selecting dB easy for 10% duty cycle applications. Selection tables already exist on our website in price books and catalogs. They are selected for 150% peak braking power for your heavy duty applications and 100% peak braking power for your normal duty applications. We provide you with a resistor part number, and we tell you whether or not you need an external braking transistor. About using dynamic braking for your duty cycles over 10%, go ahead and contact Yaskawa. We'll be happy to help you out. Let's move on to the R1000. The R1000 can be used on any drive that has full power access to the DC bus. This means the A1000, the V, the J, the L1000, and the G7 are all supported by the R1000. The R1000 is dual power rated. It has a standard rating and a continuous rating. The standard rating is for intermittent regen applications. It has a 100% power rating at a 25% duty cycle. That's 60-second max on time every 240 seconds is what it can do for regen. The R1000 also has its continuous rating. It's 80% continuous rating for constantly regenerating applications. Lastly, be sure the peak regen is less than 150% overload for less than 30 seconds. So what does this all mean exactly? How do I size the R1000? So let Yaskawa make the complicated simple. Here are the common applications list we looked at a while back, but I've broken them down to standard ratings versus continuous rating applications. As you can see, the continuous rated applications are only used for constantly regenerative applications like unwinders and test dynes. Anytime you have a break in your regen, you can consider using the standard ratings. So light and medium and heavy duty applications when it comes to regen should use your standard rated R1000. To make this easier for you, by the end of the month I will publish an R1000 selection guide. In that guide we'll offer standard use tables, standard rating tables, based on motor power. The table will list the part numbers needed, the R1000, the fusing, the reactors, etc., as well as the quantities of each. There will also be a continuous power rating. This shows the exact horsepower each package can handle continuously. So let's go through a quick example of how to size an R1000. Here's a solid bowl centrifuge. The application itself is split into 4 3-minute segments. You have your acceleration time, steady state operation, decel, and idle time. The only time regen occurs is a 3-minute block during deceleration. Now if we go back to our application selection table, we'll see that solid bowl centrifuges are listed under the standard ratings table. So we know right off the bat we can use the standard rating of the R1000. But let's dive in a little bit more. So we know the motor is a 40 horsepower motor. So we'd like to use at the worst a 40 horsepower R1000. We know our peak regen power is 36 kilowatts, or 48.26 horsepower, That's less than our 40 horsepower R1000 150% overload rating. The duty cycle in this case is 25%. So just based on these two pieces of information, we know we can use the 40 horsepower standard R1000 package. However, the R1000 is a regen only product. If we extend out the decel time, we can drop that peak regen requirement. Doing so will reduce the cycle time, i.e. less production is going to come out of the centrifuge. So you don't necessarily want to extend out that decel time. You want to produce as much as you can. So the 40 horsepower package is likely what you want to use. But if you do want to extend the decel time, you may be able to go with a smaller R1000. In addition to extending the decel time to produce that peak regen power, there are also other considerations that impact size of the R1000: motor efficiency, drive efficiency, system losses, mechanical losses, etc. We're not going to talk about that here today, but just be aware there's conditions in the system that can affect the size of the R1000. So going to our standard rated components list, we can go down to 40 horsepower, and we see that we need an R1000, a 28 amp R1000. We need two reactors that are actually the same reactor itself, fuse holders and fuse itself. So in this case, we're actually using the same reactor for the power coordination and the suppression reactors. This is not always the case, but it can happen. When you do see this, it's not a typo. It's just what the configuration requires. So let's see what we're actually saving. Let's assume a minimum drive of 5 years. Based on the previous slide, we have 2,000 hours of operation per year. Where do I get that? So if we go back to this slide, operation time, we see that we're running one shift a day, 8 hours per shift, 5 days a week. 8 times 5 is 40. 40 hours a week. 50 weeks in a year is what I'm using in this estimation. So 40 times 50 is 2,000 hours. So again, we have 2,000 hours per year, minimum 5-year drive life. It's a Yaskawa product, so it's probably going to go way beyond that. But we got 10,000 hours of operation within that 5-year span. To calculate the energy usage, it's essentially half the peak power times the amount of time you're in regen. So in this case, that's half 36 kilowatts times 25%. That's our duty cycle. That's the amount of time we're in regen. Times the total time that we're in operation, 10,000 hours. That gives us 45,000 kilowatt hours. At 8 cents a kilowatt hour, that's $3,600 for one shift. Most facilities, manufacturing plants not only have one shift, but they have 2 shifts. So if we do the analysis for 2 shifts, that's $7,200 in savings just by introducing an R1000. There's our standard rating application example. So now let's look at a continuous regen application. Here's an unwinder. Constant tension winder, we'll see constant regen. Pretty straightforward. We have a worst case continuous regen load of 40 horsepower. The regen overload will not exceed 150% of that 40 horsepower capability. So we know we need to use a 40 horsepower continuous regen package. In this case, it's realistically the same package: 28 amp R1000, 2 142 reactors, some fusing, and some fusing holders. But down to why we're using this, what are the benefits? In this case, we've calculated $8,800 per year in savings. Now, what does that really mean? So we're talking about less than 1 month to pay back the cost of the R1000 over a resistor package. So very quickly, you're paying back the additional cost of the R1000. Less than 5 months to pay back the cost of the overall R1000 package. And less than a year to pay back the cost of the entire drive solution, the R1000 package plus the drive running the motor. Additionally, we're eliminating safety issues associated with resistors. So all that heating and the fire risk is eliminated because we're now taking that energy and putting it back onto the line. Let's take a look at the D1000. Similarly to the R1000, the D1000 can be used with any drive with full power access to the DC bus connections. Again, that's the A1000, the V, the J, the L, and the G7. Just to reiterate, the D1000 operates at near unity power factor with less than 5% current harmonics during rated power conditions. Again, it's fully regenerative, otherwise we wouldn't be talking about it today. When it comes to sizing, Yaskawa has made the complicated simple yet again. Kits have been set up to eliminate the need to order each part. Each kit includes the required D1000 filters and reactors. So a question may pop up in your mind. You got kits for the D, why are there no kits for the R? We have several customers within that like to supply their own reactors, so we offer the R1000 and they can source their own reactors. The D1000 is a little bit different. We need to make sure we use the components we specify, so the D1000 comes as a kit. So how do we size the D1000? The D1000 must supply both motoring and regen power. Again, both power conditions go through that D1000. So the maximum power is determined by the maximum of the motoring or the regen condition. That can be motoring or regen, but it must be the max of both. So for example, we have a motoring power of 75 horsepower. In regen, we're actually going to do 100 horsepower worth of regen. So in this case, we want to make sure we don't just size to the motor, which is 75 horsepower. We want to use a D1000 that's 100 horsepower. Again, a one-to-one configuration is possible, but common bus applications are best for the D1000. I'd suggest the U1000 for most one-to-one configurations. So how do I select the D1000? You want to reference the total recommended motor load column. This column automatically accounts for your system losses, your drive losses, your motor losses, your mechanical losses, etc. If you know your mechanical losses, your motor losses, your drive losses, so forth and so on, you can use the max output columns to size your D1000. But if you don't know it, just focus in on the recommended total motor horsepower load column. Let's look at two similar systems here. Again, I mentioned the D1000 can do a one-to-one configuration and it can do a common bus. So let's assume we have 130 horsepower motor in a one-to-one configuration, and then we also have a D1000 feeding a DC network of three 10 horsepower motors. So I've made it simple on myself. They're both totaling 30 horsepower. So in this case, we want to use we go to our recommended total motor load horsepower column, slide down to 30 horsepower, and we see we need the D1000-240-30 horsepower. Finally, we get to the U1000. The U1000 has many features and benefits. Again, see our YouTube video at yaskawa.com for more details. I keep saying the U1000 over the D1000. Why? Well, here it is. 70% less wiring, 65% less size, 80% less weight. It's more efficient. It's a simple 3 wires in, 3 wires out. What's more to want? The U1000 can run your motor on any application. But here's a list of common U1000 applications. Some are harmonic specific, some are regen specific, and some need both. An application brochure is available at yaskawa.com that goes over these applications in some more detail. So how do I size the U1000? Well, just like an A1000. The U1000 has normal duty ratings and heavy duty ratings. Unlike regular drives that have to focus on power and current when they size their drives, the U1000 need only be sized based on its current rating. Just make sure your maximum continuous current is less than or equal to the drive's output current rating, and you're done. The last item to note is impact loading. The Matrix drive has that 150% overload for 60 seconds and can operate with impact loads of near 200% of its heavy-duty rating. I want to close with a quick overview of our regenerative products. Our regenerative products come in 230 volt and 460 volt. 600 volt is not available. We do have an A1000 high horsepower regenerative product package. So our A1000 HHP is capable of 600 volt. Those are modular based, and they start at 400 amps all the way up to, I believe, 2000 amps. Getting back to the R, the D, the U, the R1000 is rated up to 140 horsepower at 230 volt, the D1000 up to 150, and the U1000 up to 100 horsepower. For 460, the R1000 is rated up to 400 horsepower, the D1000 up to 750, and the U1000 up to 800 horsepower. So let's go through a summary of the ratings themselves. The R1000, as we mentioned a couple times, is rated based on power. It has a standard rating of 100% power and a continuous rating of 80% power. Along with that comes 150% power overload for 30 seconds. The D1000 has a 100% continuous rating for both motoring and regen. Along with that comes 150% overload for 60 seconds. Just like a drive, but in this case based on power. Speaking of drives, the R1000 and D1000 still need a drive to run that motor. Just keep that in mind. Unlike the R and D1000, the U1000 does not need separate equipment. The U1000 has 100% continuous motoring or regenerative power capabilities with 150% overload. Did I mention it also runs a motor? The D, the R, the U all use the same industrial keypad as our other industrial products like the A1000 and P1000. For the R1000 and D1000, there is little to no programming required for the drive's options. Now, I mentioned the D1000 regulates a DC output, so you can actually set the regulation level for the D1000, but that's about it. Everything else lies in the connections. For the U1000, we need a little bit more control since we're also running a motor. However, the U1000 has the same control methods, parameter structure, and capability as the A1000. I like to say that if you already know the A1000, then you already know how to use the U1000. In addition to programming, the matrix drive comes equipped with all the standard I/O and expansion modules of an A1000. Again, the key takeaway here is that the I/O capability is the same as the A1000. There is one big difference between the A and the U. The U1000's functional safety rating. The U1000 carries an improved functional safety rating. The A1000 is only performance level D, safety integrity level 2 rated. The U1000 instead is PLE, performance level E, and SIL 3, safety integrity level 3, functional safety rated. This is the highest usable rating for drives. The R and D1000 also have I/O, just enough to provide you an interlock between the drive running the motor and the D or R1000. You really don't want to try to run the drive if the D or R is not set up to operate. Getting back to what they all share, the U1000, R, and D can connect to all these networks. Each unit already has built-in Modbus RTU capability, but they can have option cards added to go online with all the popular networks. Anyone familiar with Yaskawa drives is familiar with Drive Wizard. This tool allows you to program, troubleshoot, and run a drive using your PC. This tool fully supports the R1000, D1000, and U1000. In summary, 90% of all regen applications have low regen duty cycles. They require less than 10% duty regenerative solutions. Therefore, dynamic braking packages are still usable on over 90% of all regen applications. If you're looking for an inexpensive regenerative package, then use the R1000. If you need a low harmonic and/or a common bus configuration, then the D1000 is where you want to go. The D1000 works great with any VFD that supports DC input. There's no restrictions to what can be connected to them. Actually, our motion side uses the D1000 all the time to power the servo amplifiers. Finally, the best all-around solution is the U1000. Go with the fastest to commission, compact, low harmonic regenerative drive in the market, the U1000 Industrial Matrix Drive. That concludes my presentation. I thank you for your time here today. Appreciate it.